Okay, into part B of the structure of the nucleus videos, and in this video we're mainly going to focus on the conservation laws within the nucleus. Okay, so now we're going to really get into this equation here, the famous Einstein relationship, E equals mc squared. So up until this point, we've always probably said, well, energy is always conserved. It can get transformed from one form to another, but the total energy is always conserved in a physics sense, and probably more in a chemistry sense. We've always said matter or mass is always conserved. So you can't create or destroy mass or matter. You can't create or destroy atoms. So in a chemical reactions, the mass at the start is equal to the mass at the end. The number of atoms at the start is equal to the number of atoms at the end. But this relationship lets us work out how energy can get converted into matter or mass, or how mass or matter can get destroyed, if you like, and turned into energy. And there's some really important implications of this. So, accurate measurements show the mass of a nucleus is less than that of its individual nucleons. The difference is called the mass defect. When a nucleus is formed from its constituents, that's the protons and neutrons, an amount of energy corresponding to the mass defect is released. Conversely, if we want to split a small atom apart, and we're just talking about small atoms here, we'll talk about nuclear fission later on with bigger atoms, but if we want to split an atom back into its nucleons, back into the protons and neutrons, the individual protons and neutrons it's made of, energy must be supplied, and the mass at the end of those protons and neutrons will be greater than the initial mass of the nucleus that we split. So the minimum energy necessary to separate a nucleus into its constituent nucleons is called the binding energy of a nucleus. The binding energy is calculated from the mass defect using EB equals delta mc squared. So let's have a look at how this happens and what happens. So let's take this simple case. I've just grabbed this data off the formula sheet, and for the sake of this, the helium nucleus here is an alpha particle. So what would happen if we wanted to take an alpha particle, also same as a helium nucleus, and split that into its constituent parts, which would be 2 protons plus 2 neutrons. So we've written a little equation, taking a helium nucleus with 2 protons and neutrons, splitting that apart to give us 2 protons and 2 neutrons. So, firstly, the mass defect would be equal to the mass of the constituents, which is the protons plus neutrons. Can't be stuff writing constituents again. Subtract the mass of the helium nucleus. So that would be equal to 2 times the mass of a proton plus 2 times the mass of a neutron, subtract the mass of the helium nucleus, which is equal to 2 times 1.673 times 10 to the minus 27 plus 2 times 1.675 times 10 to the minus 27, subtract 6.645 straight from that table on the other side, and we get, in that case, we have a mass defect of 5.1 times 10 to the minus 29 kilograms. We put that into the energy, the Einstein relationship, to work out the binding energy, and we get that that is equal to 5.1 times 10 to the minus 29 times by the speed of light squared, and that works out to be 4.6 times 10 to the minus 12 joules. And that might seem really, really small, but remember this is just from one nucleus. And to give it maybe some context, if we convert that to electron volts by dividing by 1.6 times 10 to the minus 19, we get that is 28.7 mega, so million electron volts. So that's a huge amount of energy to come from one single nucleus. Or we would need to put in this case, a huge amount of energy to split this nucleus into its constituent protons and neutrons. Okay, let's look now at the other conservation laws in nuclear reactions. So we've just really said that in our traditional understanding of conservation of energy and conservation of mass, they don't really apply in nuclear reactions. In nuclear reactions, the total mass of the reactants is different from the total mass of the products. However, in a nuclear reaction, the total energy, so that's the energy of the particles plus the energy associated with their mass, is conserved. Hence, the energy absorbed or released in a reaction can be calculated from the difference of masses in the products and reactants. We've already done that. So we've now got to think of mass and energy being interchangeable and that total energy associated with them as being conserved. However, some of our other conservation laws still do apply. Charge is still always conserved. So the total charge initially must equal the total final charge. And the number of nucleons is conserved. So protons can turn into neutrons and neutrons can turn into protons, and we'll learn a lot more about that in the next subtopic. But the total number of protons and neutrons must be conserved. Now, most importantly, in a nuclear reaction, momentum is conserved. So momentum is like our ultimate conservation law. And probably the hardest part of this subtopic, which I'm going to go through now, is this final dot point here, explaining using the law of conservation of momentum why a particle of relatively small mass that is emitted by a nucleus acquires most of the kinetic energy released in the reaction. So let's take this example where we have uranium-238, and that is going to emit an alpha particle or a helium nucleus. We'll cover why that happens more in the next subtopic, but for now let's just look at this nuclear reaction here. And what we're going to show is using conservation of energy why the helium ends up with most of the kinetic energy in this case. So we'll assume that the uranium is initially stationary, so its total initial momentum is 0, so the total initial momentum is 0, and afterwards the total momentum equals the momentum of the thorium plus the momentum of the helium, which is equal to the mass of the thorium times the velocity of the thorium plus the mass of the helium times the velocity of the helium. And we know that the relative masses here of the thorium is 234 from its mass number times the velocity of thorium plus the mass of helium, which is 4 times the velocity of helium. So the law of conservation of momentum tells us that total initial momentum is equal to the total final momentum. So sometimes we write LOCM, law of conservation of momentum, is where that's come from. So that means that 0, the total initial momentum, is equal to 234 times the velocity of thorium plus 4 times the velocity of helium. Rearranging there, we get, don't need that line yet, but I'll need that line in a sec. 234 times the velocity of thorium equals 4 times the velocity of helium. Let's divide both sides by 4, and we can see that cancels, and we get left with the velocity of the helium is equal to 58.5 times the velocity of thorium. We're not too worried about the sign, that's just telling us it's going in the opposite direction. For using energy, though, we just need to know the relative amounts of the velocity, which is where we're going to go to next. So we know kinetic energy equals half mv squared. So if we work out the relative kinetic energy here of the thorium, will be equal to a half times the mass of the thorium times the velocity of the thorium squared, and the kinetic energy of the helium will be equal to a half times the mass of helium times the velocity of helium squared. So we know the mass of the thorium relative to the helium is 234, and its velocity in this case is 1 relative to the helium, the way we've worked it out. And the kinetic energy of the helium in this case is a half times by the mass, which is 4, times by its velocity, which is 58.5 squared. So if we work that out, we show that the kinetic energy of the thorium in this case is 117, and the kinetic energy of the helium works out on that for it to be 6,844.5. And so if we work out the relative amounts here, so in that case, what's the kinetic energy of the helium divided by the kinetic energy of the thorium? 6,844.5 over 117, and that works out to be, related to the original velocity, 58.5. So the kinetic energy of the helium is 58.5 times greater than the kinetic energy of the thorium. So you can see that they're actually related by that velocity. You can show that in a more algebraic way if you like, have a go if you want to, but going through that process I think is more than adequate way to show that relative amounts of the kinetic energy based on the conservation of the momentum, which is where we started. But if you can do that, if you'd like to do that in a more detailed way, you're welcome to try, but I didn't want to over confuse you. Hopefully that makes it nice and clear. So into the final part, which is the application, which is the production of radioisotopes. This subtopic really ties into what we looked at earlier in the year when we looked at a cyclotron, and also what we're going to look at in the final subtopic when we look at a nuclear reactor. So it's really about the production of new radioisotopes, which are mainly used for medical purposes. So hydrogen or deuterium, so both hydrogen isotopes, which can be stripped or added to electrons to give them a charge. Therefore, they can be accelerated because of their charge in a cyclotron. As we learnt before, they get fired at another stable nucleus, and then that reaction that occurs produces two unstable isotopes, which are used in things like positron emission tomography or PET scanning that we covered when we looked at the cyclotron. So really what we're learning in this topic is about how to write balanced equations for those reactions, and hopefully from what we've done now and what we'll do in the next subtopic, you'll become very confident with writing those. The top one here is looking at firing a neutron into a sulfur isotope to make a new isotope. Obviously neutrons don't have a charge, so they can't get fired, accelerated in a cyclotron. But when we look at nuclear fission, and particularly how a nuclear reactor works in the final subtopic, we're going to learn how we produce a stream of neutrons which we can fire at something like a sulfur atom to produce the phosphorus-32 isotope here. So we'll sort of finish the story of this one when we look at the final subtopic.